this new Google quantum computer that can do essentially the way a quantum computer works, a problem that would take thousands of years for every computer on Earth to solve.
I've read that.
It can solve in a second.
The head of Google's quantum computing division just told the world that their new chip might be proof we're living in a multiverse. That every time it runs a calculation, it's borrowing computational power from parallel universes. He wasn't joking. He published it in an official Google blog post, and the scientific community went to war over whether he'd lost his mind or stumbled onto something genuinely terrifying. December 2024. Google announced a quantum chip called Willow that completed a calculation in 5 minutes, a calculation that would take the world's fastest supercomputer 10 septillion years. That's a 10 with 25 zeros behind it. The universe is only 13.7 billion years old. This number doesn't just exceed the age of the universe, it shatters every known timescale in physics. And Hartmut Neven, the guy who built it, looked at those numbers and said the quiet part out loud. This performance is so impossibly fast that it might only make sense if the chip is reaching into other universes to finish the calculation. Some scientists nodded. Others called it the most irresponsible thing a tech executive had ever said. Google's stock jumped 5%, and suddenly everyone wanted to know what the hell Google had actually built. So let's break down what really happened, because the truth is somehow weirder than the headlines. Here's the thing about quantum computers that nobody tells you. They've been theoretically possible since the 1980s. We've known how they should work for decades, but there's been one problem blocking the entire field, and it's brutal. Regular computers use bits, ones and zeros. Quantum computers use qubits, quantum bits that can be 0, 1, or both at the same time. That superposition is what gives them their power. They can explore multiple solutions simultaneously, like running every possible path through a maze all at once. Sounds perfect, right? Wrong. Because here's the catch. The more qubits you add to a quantum computer, the more errors you get. It's like trying to juggle 1 ball, easy. 2 balls, still manageable. 10 balls, like you're dropping them everywhere. 100 balls? Forget it. For 30 years, every time researchers built a bigger quantum computer, it just got noisier, more unstable, less useful. They needed error correction, a way to add more qubits while keeping errors under control. But every approach they tried made things worse, until Google built Willow. They designed a chip with 105 qubits arranged in a lattice where some qubits store data while others constantly check for errors and fix them in real time. It's cooled to temperatures colder than outer space, 20 millikelvin, which is barely above absolute zero, to keep the qubits stable. And when they scaled it up, something happened that shouldn't have been possible. Errors went down. More qubits meant fewer mistakes. They'd crossed what physicists call below threshold, the point where a quantum computer actually gets more accurate as it grows. After 30 years of failure, Google had finally cracked it. That alone would have been the story. A genuine breakthrough published in Nature. Verified. Peer-reviewed. Real. But then they ran the benchmark test. And that's when things got strange. Google tested Willow using something called random circuit sampling. It's basically a torture test designed to push quantum hardware to its absolute limit while still being verifiable by classical computers. Willow finished in under 5 minutes. A classical supercomputer? 10 septillion years. Let me put that in perspective. The universe has existed for 13.7 billion years. This number is 700 trillion times longer than that. It's not just big. It's physically meaningless. There aren't enough atoms in the observable universe to even represent that number properly. And Hartmut Neven looked at this result and made a choice. He could have talked about error correction. He could have focused on the engineering breakthrough. Instead, he wrote this. This mind-boggling number exceeds known timescales in physics and vastly exceeds the age of the universe. It lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse. The internet exploded. Nevin was referencing physicist David Deutsch, who proposed back in 1997 that quantum computers don't just calculate in our universe. They reach across parallel universes, borrowing computational power from countless alternate realities. Every qubit in superposition exists in multiple states simultaneously, and in Deutsch's interpretation, each state corresponds to a different universe. When Willow runs according to this theory, it's not just computing here. It's outsourcing pieces of the calculation to infinite parallel versions of itself, then bringing back the answer. Nevin was suggesting that Willow's performance was so far beyond what should be physically possible in a single universe that the multiverse theory might actually be real. Scientists lost their minds. Some researchers were on board. Andrew Cleland at the University of Chicago called it a signature result. John Preskill noted that Willow was now operating in computational spaces classical computers literally can't enter. The math was verified. The error correction was peer-reviewed. This wasn't pseudoscience, but the multiverse claim? That's where the knives came out. Critics pointed out that Deutsch's many worlds interpretation is just one way to explain quantum mechanics, and it's not even the most popular. The Copenhagen interpretation and neorealism both explain quantum behavior perfectly without needing parallel universes. Willow's performance fits standard quantum mechanics just fine. No multiverse required. Physicist Sabine Hossenfelder went harder. The particular calculation has no practical use, she wrote. It's a benchmark designed to show speed, not solve actual problems. This is marketing dressed up as physics. She reminded everyone that Google made basically the same claim in 2019 with their Sycamore chip, and IBM later proved a classical computer could handle it under the right conditions. Same playbook, different chip, same hype. Even supporters admitted Willow's nowhere near ready for real-world use. The error, rates it achieved, 0.14% per cycle, are still orders of magnitude worse than the 0.0001% needed for useful algorithms. We're talking about needing millions of qubits before this thing does anything commercially relevant. So why did Google's stock jump 5%? Because investors don't care about the multiverse debate. They care about one thing. Google just proved that scalable quantum computing is possible, that the fundamental barrier everyone thought was insurmountable might actually have a way through. And that changes everything. Here's what nobody's talking about. Whether or not Willow touches parallel universes doesn't actually matter. What matters is what comes next. In October 2025, Google followed up with Quantum Echoes, an algorithm that runs 13,000 times faster on Willow than the best classical supercomputer. It can measure molecular structures with precision we've never had before. That's not a benchmark, that's a real application. Chemistry, materials science, drug discovery. These fields are about to get hit with a computational tool that operates on a completely different level. And here's where it gets uncomfortable. Right now, Willow is a prototype with 105 qubits. Google's targeting 1,000 logical qubits by the late 2000s. IBM, Microsoft, Amazon, they're all racing to the same milestone. Whoever gets there first unlocks something we're not ready for. Because at that scale, you can simulate molecular interactions perfectly. You can model chemical reactions before they happen. You can predict material properties before you synthesize them. And you can break encryption. Google said Willow can't crack modern cryptography. They're right. It would still take multiple lifetimes of the universe to break RSA encryption with 105 qubits. But estimates say we're about 10 years and 4 million qubits away from that threshold. 10 years. That's it. And the National Institute of Standards and Technology is already scrambling to develop quantum-safe algorithms before that deadline hits. The security community knows what's coming. They're just not sure if they can build the defenses fast enough. So here's where I land on this. Forget the multiverse theory for a second. Forget whether Deutsch was right. Focus on what actually happened. Google built a machine that performed a calculation so far beyond classical computers that the numbers stopped making physical sense. They proved that quantum error correction can scale. They demonstrated that this technology is moving from interesting experiment to actual capability faster than anyone predicted. And when Hartmut Neven suggested this might be evidence of parallel universes, he wasn't just hyping his product. He was pointing at something deeper. We've built machines that operate on principles we still don't fully understand. We've got the math. We can build the hardware. But the fundamental why of quantum mechanics remains a mystery. 3 major interpretations of quantum physics all explain Willow's performance. One says parallel universes. One says superposition collapses into a single reality when measured. One says the universe is fundamentally probabilistic with no hidden variables. They all work. They all fit the data, and we have no way to prove which one is actually true. So we're building incredibly powerful technology on top of a foundation we don't completely understand, and that should make you uncomfortable. Because whether Willow touches other universes or not, we're crossing into territory where the tools we're creating exceed our ability to predict their consequences. 10 years from now, quantum computers might cure diseases. Or they might crack every encryption system protecting global infrastructure. Probably both. The multiverse debate is a distraction. The real question is whether we're building the safeguards fast enough to handle what's coming. Because Willow isn't the endpoint, it's the starting line. And the race just started.